high rad mixtures with high rad content in terms of low temperature cracking, fatigue cracking, and moisture-induced damage. This is the presentation outline. I'll talk a little bit about introduction. What is RAP? RAP is reclaimed asphalt paving, recycled asphalt. Recycling of asphalt, the RAP is generated when they mine old pavement, and then they move the RAP to landfills. According to EPA and FHWA, more than 70 million tons of RAP is recycled every year. About 80%, which makes it like the material number one to be recycled in the US. And it saves like $1.8 billion every year and hundreds of acres of landfills. My project is about high RAP, not RAP. What's the difference? When we talk about RAP, RAP is whatever less than 20% RAP in the new mixture. Anything above the 25% is called high RAP mixture. Actually, the recycling is like, they start recycling from 1970. The DOTs nowadays are very comfortable with recycling low content of RAP, less than 20%. But at the low RAP content, the blending between the binder of the RAP and the virgin binder in the mix, it tends to make the mixture stiffer. The amount of stiffening at low RAP content will not affect the overall behavior of the material. However, at high RAP content, the blending and the stiffening of the material will be significant. In my project, I was using plant-produced mixture instead of patching in laboratory. What's the difference? The regular procedure of research is doing patching in laboratory. They make sieving, and then they add the RAP, they add binder, and then they mix. So they prepare the mixture in the lab. However, the blending between the binder in the RAP and the virgin binder depends on a lot of things happen in the plant itself. So it depends on the mixture type, the amount of mixing, the temperature of mixing, and the plant type. So all this stuff, if we are using patching plant in laboratory, will not be representing the real pigment. The material I used here, so I used material from 3 different states, New York, New Hampshire, and Vermont, by 2 different companies, and I used 2 different plant mixture from patch plant and drum plant. And I used 4 different binder grades, which is the grading by superpave to the binder, and I used different amounts of RAP in the mixtures. So I used the 0, so it's virgin, all the material is virgin, and then I used the 20%, which is the regular practice nowadays, and then I want to see what will happen if we use 30% or 40% instead. What is the problem of RAP and what's the problem of stiffening the material? Material which is stiffer will tend to crack faster. So low temperature cracking, fatigue cracking will be a big issue. Also moisture damage. This is a moisture damaged pavement, and this is the new pavement. So those 3 points is very significant when we talk about RAP and more stiffer material. However, rutting is not very significant here because stiffer material tend to resist rutting more. And also, this project was especially for northeast of the US, and the northeast is colder region, as you know, and rutting more susceptible in hot regions. This project was pooled fund project, and we were working with North Carolina State University, UMass Dartmouth, and Rutgers University, Pike Industries Recycling, and FHW. So this is the overview of the project. I want to talk about the viscoelastic behavior of asphalt mixture. Actually, when we talk about any civil material we used to use, it's elastic. So the deformation depends on the stiffening, the stiffness of the material, and the applied load. However, asphalt is viscoelastic material. So it's not pure elastic, it's not pure viscous, it's something between. And it depends on the temperature. So we call it thermo-viscoelastic material. At lower temperature, it tends to behave like rubber. At higher temperature, it tends to be a viscous fluid like honey or any viscous fluid. It's not only depending on temperature, but it also depends on time of loading. So we are not only concerned about the magnitude of loading, but we are concerned about the time of loading. Because the response of the material after 1 hour, for example, here at 25 degrees C will be that much. After 10 hours, it will be that much. So the deformation, for example, under any load will be dependent on time of loading itself. So now we have 4 things. We have the magnitude of loading, we have the temperature, we have the stiffness of the material, and we have the time of loading. So when we test this material, we need to control the load or the deformation, plus we have to control the temperature and the time of loading. That's why, for example, to test a viscoelastic material, for example, we have creep test, we have relaxation test, we have frequency sweep test. All these tests is controlling temperature and controlling time of loading. Here we apply in creep test, we apply constant stress, and the strain will increase with time. At relaxation, we apply constant strain, and the stress will decrease by time. In frequency sweep testing, we apply sinusoidal loading, and so the stress will be sinusoidal, and then the strain will be shifted a little bit from the stress. There is time lag, which is another property of the viscoelastic material, between the stress and the strain. So these are the testing we used to do for viscoelastic material. Preparing specimen in lab, as I said, I get the material from the plant, it's mixed in the plant. I get it in a bucket, steel bucket, airtight, and then I reheat it in the lab for 2 hours, following protocol by North Carolina State University. And then we compact the material. As we see here, when I compact by the gyratory compactor, I adjust the height and the weight so that I can get 6 plus or minus 0.5% of air bubbles. After that, I want to talk about first test I'm doing is the creep test, which I use the first specimen right here. So the creep test, as I said, I will apply constant stress and I will read the strain, and I expect the strain to go up a little. This video is made by ITC. I just edit the video to be compatible with my presentation. This is the machine we used. This is a servo-hydraulic machine. Actually, up here is a load cell to control the load, and then this is a temperature chamber to control the temperature. Then this is the jakes to apply the load. We use nitrogen gas to cool down the temperature chamber, and this is the jakes, and we put the specimen like this one inside this jig, so it's indirect tension test. We apply compression in the vertical direction and we get tension in the horizontal direction. Then we mount LVDT, linear variable transducers. And actually in the picture this is a resistive transducer, but we put LVDT on the specimen. And then we read the testing, we read the vertical and the horizontal deformations on the specimen. The testing details is loading time will be for 100 seconds, so we control the time here for 100 seconds. Temperature, I will repeat the same test at 0, -10, -20 degrees C, and then 3 replicates are used from each mixture. I have 18 mixture, so I have 3 replicates times 18 mixture, and I do them at 3 different temperatures. The other thing I have is, which is very picky here, is choosing the load. I'm not choosing the same load for all the mixtures and all replicates, but I just choose the load which give me a strain, horizontal strain, not more than 300 microstrain and not less than 50 microstrain. And what is that? Why is that? The 300 microstrain, above this limit, the material will not be linear viscoelastic, it will be non-linear. So I want to avoid this non-linearity, so I have to be under the 300 microstrain limit. And why it should be more than 50 microstrain? To differentiate between the signal itself and the noise in the system. The other thing I want to talk about, after I do the creep test, there is something called superposition concept to construct the master curve for creep. Again, the same picture, I like this picture actually. In this picture, I said that the behavior of the material will be depending on temperature and time, but there is something else called time-temperature superposition principle, which means that the response of the material could be the same here under high temperature with short loading time versus lower temperature and longer loading time. So I can shift the curve. Those are the 3 curves I get from 0, -10, -20 degrees C testing, and then I can shift them using the time temperature. And instead of talking about time, I use something called the reduced time, which is something imaginary, so that I can take in consideration the time temperature superposition. After constructing master curve and applying the superposition concept, there is some relation between viscoelastic material properties. As I said, there is creep test, there is relaxation test, and there is dynamic modulus from cyclic loading. Actually, the 3 properties are material properties, so they should be related. So actually, there is some mathematical models to predict or to use them interchangeably between the 3. So the other thing, after I get the creep data, I predict relaxation, I predict dynamic modulus, and after these predictions, I have the 3. So what's the reason of all this? Why I'm doing all this stuff? Going back to the title of the research, it's testing the performance of these materials in terms of low temperature cracking and fatigue cracking. So I will use the creep compliance in a low temperature cracking model, and then I will use the relaxation modulus in fatigue cracking model. So now I have the low temperature and the fatigue. Why do I need the dynamic modulus? The dynamic modulus, I get the data for the dynamic modulus from Rutgers University, and they have a machine which can't go to -10 or -20 degrees C. It only go down like to 4 degrees C. So I use actually the dynamic models predicted from the creep at low temperature to continue to complete the dynamic models master curve using the superposition concept which I just talked about. After that, I want to talk about the low temperature cracking model and the fatigue model. The low temperature cracking model, the low temperature cracking is very nice cracking. I like it because it happens like at same spacing. So you will have a pigment and you will find nearly the same distance between each crack and the other crack. It's something nice. It's strange to like a crack, but I like to study the crack, not the crack itself. And then this is the model for the crack. Of course, that tensile strength coming from contraction of the pavement. Actually, this part tends to contract. That's why the stress happens. And the stress will be higher at the top of the pavement. Neither the stiffness or the strength of the material can characterize the cracking properties. Now I have the stiffness from the creep test, but I don't know what about the strength. Why neither one of them can help me with working on the cracking model? Because like high strength material may not crack if the material is flexible, and like lower, like weaker material will not crack if the material is not very stiff. I'm sorry. The material, like the crack will, if the strength is great, stiff material will not crack, and if the material is weaker, the stiffness. If the material is weak, it will not crack if the stiffness is not so high. So besides having the creep compliance test, as I said, I have to do a low temperature tensile stress. It's also on the same specimen, doing IDT test again, but it will be at negative 10 degrees C, and I will apply monotonic loading until cracking of the specimen. So this is the low temperature cracking. For the fatigue cracking, the advantage of having the model is to get something called the characteristic curve C versus S, which describe how the damage will propagate in the material, or how the propagation of the damage will affect the overall stiffness of the material. This characteristic curve is very good because it's not depending on the type of loading or on the frequency of the load or anything. It should be the same. Whatever is the cyclic versus monotonic, or the amplitude of the frequency or of the loading, it will end up with the same curve. Using the superposition concept, I can shift this curve and I can get the properties of the material at any other temperature. So if you need to know the properties of or the shape of this material or pavement at certain temperature, after 10 years under certain traffic, you can know what damage will happen to this by using the characteristic curve. Using the characteristic curve will be using the model called simplified viscoelastic continuum damage approach. The continuum damage approach is just, instead of looking at the micro cracks in the specimen, I will deal with the overall material, and I will say that the stiffness of the overall stiffness of the material will go down by the micro cracks when the micro cracks happen. And there is something else called the correspondence principle, which changes the viscoelastic problem to elastic problem. I can apply Hooke's law, for example, by, instead of using the real stress, the real strain or the real stress, I will use imaginary or pseudo strain. So by using the imaginary or pseudo strain, I can apply elastic problem like Hooke's law and any other properties of elastic problem. This is made by Hampshire. This is the testing using the AMPT, and I will do it at 10 Hertz cyclic loading, 25 degrees C, until fracture of the